Hello everyone and welcome back to another video. Today we are looking at NKT Photonics, one of the basic infrastructure providers in the whole quantum revolution, or as other people say, one of the shovel sellers in the gold rush of quantum. And if you are interested in what they are actually making in terms of products, then stay tuned for today's video because we are looking into NKT Photonics. But before that, a very quick thing. If you haven't subscribed to this channel yet and you are interested in learning about companies that are actually contributing to the quantum revolution, to the new technology, quantum technology inventions, then make sure to subscribe to this channel right now. It's just a click of a button and you will not miss out on the next video. But now let's hop right into their website as per usual. So here we are at the website. It says NKT Photonics. High quality optical fiber and laser technology for your innovations. Interesting. I don't see quantum here, you might think. So, moving on, it says solutions for innovators. Visionary companies and institutions are changing the world through their innovations. Through optical fiber and laser technology, we deliver the state-of-the-art solutions you need to push the boundaries of what's possible. Solution for innovators. And then you see a couple of known names here like Leica, NASA, Harvard University, but you also see Quera Computing, which we have featured already in the Hidden Quantum Champion series before. So you see players from various different markets. And I mean, already lasers themselves, you might think, are quantum applications, and you're probably not wrong. But I mean, Quera Computing as a quantum computing provider is then probably the second generation of quantum applications. So what do they actually make? What are the products? We see here the Super K series, super continuum white light lasers. Super K series is an industry-leading range of turnkey supercontinuum white lasers. So a white laser, as the name indicates, is white light is not just one source of light, it's a mix of different colors of light. So it's a continuous spectrum. And you might know from the laser pointers at home or in school that there's like red ones, there's green ones, there might be blue ones as well, right? And if you're combining multiple of these colors, you would eventually end up with white light. But white lasers are still comparatively new, I would say, in terms of spectral availability, especially if you're thinking about continuous light as what this super continuum here indicates. Because if you are mixing RGB, if you have lasers with RG and B color channel, you would technically have white light. But practically it's still only 3 different light sources, so it's not continuous. It's very like looking at the color spectrum, you still have only 3 colors in there. Like for example for LEDs, whereas you want to have a continuous spectrum for continuous laser. But yeah, I'm not an expert on that, so maybe I'm completely off with that as well. Then we have the Cohera series single frequency fiber laser, which I guess is interesting for all the fiber applications, telecommunication and whatnot. And then the Origami series for femtosecond lasers. So femtosecond lasers are lasers that can make very short pulses, and there are different reasons, different applications where these super short pulses are interesting. Finally, we have a little news section down here. I'm recording this in March 2026, so you see it's pretty much up to date. Last news is from 19th of March. Integrated fixation stimulus channel for retinal imaging. Adaptive optics is reshaping retinal imaging. A compact fixation stimulus channel delivers eye control and pure light. Finally, there is some, let's say, quotation down here and a link to upcoming events. And then we are already at the bottom of the page. It says NKT Photonics, a Hamamatsu company, so Chinese group that is owning this, Japanese group. Japanese group that is owning this company. Good. Now, is this everything I want to talk about with you today? No, of course not. So if you're clicking here, we see there is some applications about nanotechnology and quantum, and I think this is where it actually starts becoming interesting. So large investments in small things have increased the demand for lasers for quantum and nanotechnologies. Quantum technology covers a range of fast-growing segments within quantum computing, sensing, metrology, and communication. Nanotechnology covers the development of advanced materials such as graphene, carbon nanotubes, metamaterials, plasmonic structures, and quantum dots. Find inspiration here, and then we have the applications there. Of course, we don't care about nanotechnology because this is not funky and trendy. We only care about the quantum world of things, and luckily this is already at the top of this page, and the nanotechnology is only down there, so we are for sure ignoring that part, right? So let's look at what the quantum application part is about. So we see here there is the barium ion control, quantum computing, atom trapping and cooling, beryllium ion trapping, dipole trapping, rubidium cooling, single photon generation, squeezed light, frequency comms, acetylene locked lasers, NV centers in diamonds, quantum gravity sensing, and then quantum inertial sensing. Now, I'm not going to go into every single one of them because otherwise the video is too long, and anyways, nobody will watch until the end. So let's only pick a couple of those. Let's start with the quantum computation part. So better quantum computers with coherent fiber lasers. Explore how coherent fiber lasers provide the precision and stability needed for advanced quantum computing applications. Get high qubit quality with coherent industry-ready fiber laser systems designed for ultra-cold atom-based quantum computers. So ultra-cold atoms, I think most of these computers that are using atomic qubits, I guess they have to be ultra-cold because otherwise you cannot control them. But I think this will probably relate to either the neutral atoms or maybe even the ions. So let's read further in. So quantum computers are one of the most groundbreaking technologies of our time, and lasers play a crucial role in quantum computing by cooling and trapping atoms to create stable qubits. Narrow line width and high power stability are essential for precise control, while fiber delivery ensures consistent beam quality. Coherent lasers offer the required wavelength, coverage, stability, and reliability for advanced quantum applications. So in the past, that was a lot of stuff that was required for these Bose-Einstein condensate type of experiments, and now this is, of course, let's say at the very ground of all of these neutral atoms and also on the ion side. So don't believe the people that are telling you don't need to cool anything when you are working on those vacuum chamber systems with atoms or ions in there, because it's a lie. You actually need to cool stuff, but you don't cool it by like attaching it to a fridge. You're also not using helium cryostats or anything like that, but you're actually cooling it by using lasers, which is anyways much cooler, right? So, using lasers for quantum computing. Cold atom systems are among the leading candidates for quantum computers. Lasers can cool atoms down and trap them in place using advanced techniques like Doppler cooling and dipole trapping, or sometimes also I think people consider optical tweezers or call it optical tweezers. These cold atoms can then be manipulated, entangled, and read with more advanced lasers and imaging techniques, creating high-quality qubits in quantum computers. Quantum computers can perform operations far beyond what classical computers can handle. They will become crucial for applications like drug discovery, financial optimization, supply chain management, and solving fundamental scientific problems. These are the promises that we, of course, also hear from the quantum computing industry that the quantum computer manufacturers are looking into. As of today, I think there's no clear existence of a quantum advantage where a quantum computer can do something, let's say, provably much better than a classical one. but we are getting closer and closer to places where it might get on par, or where actually quantum computing becomes an interesting alternative to look into. So pick the right laser. When picking a laser for atom trapping, cooling and manipulation, there are several things to consider: narrow line width and power stability, fiber delivery, wavelength coverage, and stability and industrial reliability. So many of them for different reasons, right? You want to make sure that your system, your quantum computer, you're not, let's say, in the stage where in a quantum computer where the laser is your let's say main focus of experimentation, right? It should just be a functioning tool, and everything else should be covered, and it should be easy to integrate and work like a reliable machine. And that's, I think, what is the promise here, and that's probably mainly what is covered by these points. Of course, it also covers like how many of these lasers do I need to buy. If I have one that can fulfill multiple purposes, that's good, obviously. It also relates to the reason of how do I integrate this, right? Do I need to build some complicated structure to get my laser in, or can I just couple it via fiber? Makes things maybe easier because you don't have to build all of these complicated optical tables that you would have in the lab. So all of that said, let's move on in the text. Why narrow line width and power stability matter. So now we actually get the explanation. When you're choosing lasers for trapping, cooling and manipulating atoms, two key factors stand out: narrow line width and power stability. Line width refers to the width of the laser's frequency spectrum. Phase noise in the system causes the line width to expand. The line width has a big impact on how well your cooling and manipulation techniques work. In Doppler cooling, for instance, the line width must be smaller than the atom's natural line width. If the laser's line width is too broad, it limits the cooling efficiency and the precision of your experiments. So quickly one step back, what is this whole line width situation about? If you take a prism and hold it towards the sun, and you might have seen that before, or maybe like a crystal or whatever, right? Then it creates this rainbow. So you see basically the whole spectrum of light that the sun is creating, which is a continuous spectrum. That's why you see the rainbow. Now, actually, if you're looking really, really close into it, then you will see that there are black lines. So there are shadows in between. It's not a continuous line, but there are actually some lines in that spectrum where the intensity of the light is much lower. These are called Fraunhofer patterns or Fraunhofer lines, if I'm not mistaken, called after their discoverer. And actually, these are caused by our atmosphere or other things. They are basically absorbing specific frequencies of the light. So an atom can absorb light frequencies, can absorb specific shades of your or specific colors, and they are very specific to the atom, and that has to do with the levels of the electrons and with the levels of molecules. If you're having multiple atoms, the molecules, they also have specific states at which they can absorb these energies, and there's a lot of research on that. So these lines, they're very well known for these different atoms. There's a lot of nuclear or atom research that has been done over the last decades to identify these different things, because they are interesting for many, many different things. For example, if you want to know what material a certain planet is made out of, or a certain planet, a moon, whatever is made out of, on its surface, you could, for example, look at what light comes from there, and by looking at the spectrum, so at the colors that you see, you can identify what is getting reflected, and thereby identify what kind of material might be in there. Or if you see a cloud somewhere in the space, you might be able to identify what is in this cloud because it absorbs specific frequencies. So that said, there are these specific frequencies, and they are like sharp lines. So they are not like rainbows, but they're like one specific color frequency, and that's what is more or less these lines that we are referring to here. And when we talk about Doppler cooling, You know the Doppler effect probably, because if you are, for example, on the street and you hear an emergency vehicle driving towards your direction, driving away from you with the sound on, you hear that the sound is changing slightly depending on whether it comes your direction or it goes away. That is called the Doppler effect, and it has to do something with the fact that when you are moving and you are emitting sound, you are basically adding something to the speed of sound, more or less. I mean, if you want to understand the exact details, I recommend you to look it up on the internet, maybe ask an AI about it and then do some more research on it. But exactly the same effect is now being used to kind of cool down atoms, to remove let's say, energy from them. And energy, in that sense, heat energy, is basically vibration or velocity of the atoms of moving in the space. So you try to take away all of their velocity so that they are almost like standing still in space. And that's done via this Doppler cooling effect. So basically sucking out energy from them using light. Now, the other thing is and for that you need a very, very narrow bandwidth laser, so something that has a very precise output of light frequency that works exactly for a specific energy level on your atom. That's how you can kind of suck out the energy. Now, power stability refers, and I'm going back to the text, right, refers to a laser's ability to maintain consistent power over time without fluctuations. Power stability is essential to maintaining consistent cooling rates and ensuring that your experiments are reproducible. Insensitive fluctuations or relative intensity noise, RIN, can add unwanted heat to your system and limit cooling effectiveness. Our fiber lasers are engineered to meet these demanding requirements. They are thermally and mechanically isolated to minimize power fluctuations with line width in the 1 to 100 Hertz range. Our lasers are the narrowest available. Then we see the wavelength coverage over versatile quantum for versatile quantum computing. So quantum computing requires lasers that can cover a wide range of wavelengths, from the ultraviolet UV to the infrared IR. Different atomic species have specific transitions in these regions. To explore their potential, you need access to these wavelengths. Our Coheras fiber lasers offer broad wavelength coverage, covering important UV, visible, and infrared wavelengths, including those necessary for ion and neutral atom-based quantum computers. This flexibility allows you to explore a wide range of atoms and develop more robust quantum systems. Okay, that's pretty much clear, I guess. Then we see fiber delivery for reliable light transmission when it comes to quantum computing, especially when scaling systems. Reliable light delivery is essential. Our fiber-coupled laser reduced power losses and maintain high beam quality over long distances. Our fiber lasers are inherently single-mode stable and mode hop off free, which is key for high-precision quantum applications. By combining these features with our photonic crystal fiber technology, you get reliable delivery of high-power, narrow line-width light without compromising beam stability. Whether you are rack mounting your laser system or using in a tabletop setup, our Aero Guide power fiber delivery system offers the flexibility you need for seamless light delivery. It's designed to transport light at all levels with unmatched beam stability. The system ensures that regardless of your setup, you get precise and consistent light delivery for quantum experiments. If you want to mount the laser system in a rack, it's not a problem. If our unique fiber delivery system, Aero Guide power, you can get light wherever you want. And then scalability and industrial reliability. With over 20 years of experience and more than 20,000 single frequency fiber lasers deployed globally, our systems are designed for scalability and reliability, and so on and so forth. What is also very interesting is down here you have the explanation. So I guess if you want to understand how Doppler cooling works, this is a good resource to check out, because there is some explanation down here of how that is actually done. And then furthermore, you see also some resources down, some links down here. Our quantum engagements, you see the European Quantum Flagship, QUIC, the European Quantum Industry Consortium, QEDC, and the Danish Quantum Community linked down here. Okay, and then, there's further stuff to read. Now, this is about the quantum computing. So I guess they're selling instruments that are very fundamental to quantum computing. There's much more here, right? You see like dipole trapping and so on and so forth. Single photon generation, I think, is very interesting for the quantum communication part of the story, right? So I think it also says here single photons can be used as information carriers in, for example, quantum key distribution schemes or as qubits in quantum computers. So there are also photonic quantum computers, right? So there, these single photon generators might be interesting. And I guess, again, you want to use laser type of sources for that. So here you see, again, some products that are linked to this. So you see the polaris diode lasers and the super K chroma tunable lasers as recommended products for that. And if this is an interesting topic for you, then go ahead and read it. There's another couple of things interesting here. So the NV centers in diamonds, we've talked about this before. There are also other companies already highlighted within the Hidden Quantum Champion series that are working on NV centers in diamonds as sensors. The other two interesting things here are the quantum gravity sensing and the quantum inertial sensing. Let's quickly check out the quantum inertial sensing because I think we haven't talked too much about that yet. But it is about measuring acceleration. And actually, I think it's also something that is being actively, discovered or actively tested in the defense use cases again, and might actually in the future also find its way into consumer type of applications because it is a very accurate way to measure acceleration. So, navigation with quantum inertial sensors. Inertial sensors are essential for accurate navigation and positioning in aerospace and defense applications. Leveraging atom interferometry for unparalleled precision gyroscopes and accelerators are examples of inertial sensors that can accurately detect acceleration and rotation. Bit hard to read the last bit because it's so bright here. So, accurate quantum inertial sensors. If you can track your rotation and acceleration in any direction over time, you can calculate your exact position and velocity relative to your standing point without relying on external inputs such as GPS or landmarks. Open bracket. This is for sure interesting for everyone in the defense sector because if you have, for example, a submarine that is going and transporting, rockets, for example, or other stuff, and you want to make sure that those can operate properly, even in zones where there's no GPS, and you hit the target that you are aiming for precisely, then those types of sensors, they actually might be interesting use cases. This is as of today. You could also think about aircraft, civil aircrafts that are flying in regions where GPS for some reason might be jammed or hard to access. That could also benefit from that, right? So just to say, there are multiple different applications and multiple different industries that might be interested in looking into this. So the accuracy of your inertial sensors determines the accuracy of your position and velocity derived from the measured acceleration. Today, the most accurate inertial sensors are based on atom interferometry, which is created by cooling and manipulating individual, typically alkaline atoms with laser beams. A popular choice of atom for atom interferometry is rubidium-87, which requires a high power 780 nanometer beam of light with narrow line width and high beam quality. So let's quickly talk about how it works. And I think there's something explained here. So Atom interferometry uses the wave property of atoms to place an atom in a superposition between two states. One state where the atom has been hit by a light pulse, and one where it has not. Something that will send the two stages along different paths. Just as light, these two states can undergo interference if brought back together. Any perturbation along their paths, such as the forces from rotation or translation, acceleration, will affect how the matter-wave interference pattern turns out. So, quick step back. This is, I think, a lot of interesting stuff happening in these couple of lines of text, and maybe also the mind-blowing power of quantum mechanics, right? So atoms, they are not just little points that are sitting somewhere in the vacuum or in the universe. They are wave functions themselves. So even the solid matter that we think about, which is atoms, they are quantum objects and they can interfere with themselves. So we know that there's interference in waves, right? If you're looking at a lake and there's two boats going by, you see the waves and they start to interfere with each other. That, I think, is a pretty well-known concept, and that's something that we see on a day-to-day basis. Now, it becomes already less intuitive when talking about light, but I think it's still something that people might be familiar with. So if you have, well, let's talk about sound. Sound is also it's also a wave, right? So acoustics. And their interference is also something that we have gotten used to. You take your headphones, you turn on the voice cancellation, and what it does is it basically records the sound that comes from the outside, creates the counter sound to that, so the anti-wave more or less, and thereby destructive interference is creating silence because it is counteracting the waves, the sound that comes from the outside. Now with light, the same thing is possible. You can have light particles, so photons, that are interfering with themselves. This is, for example, done in interference or interferometer type of setups. And there you can see that by tuning the light in a specific way, you can have these interference patterns. Now, very interestingly, this is not only true for light, but it is even true for matter itself. And you can use basically atoms to do this type of interference experiment. To be more precise, not only atoms, but even the most fundamental particles, so even electrons. And that's why there are things like electron microscopes. And in electron microscopes, you don't use light, but you actually shoot electrons at something and watch their interference pattern. So watch how they interact with the material, how they do certain interference type of interactions, and thereby you can reconstruct what the object looks like. And the wavelength of an atom or of an electron is much shorter than the one of, for example, UV light. And that's why you can use these kind of instruments to see very tiny things, even down to atomic resolution scaling, more or less. And now they are saying they built an interferometer, so a system that kind of creates two states of an atom. In this case, one excited state where you have maybe like an electron sitting in a slightly elevated level, and when it falls down, it creates some light, and one non-excited state where this is not the case. And now you're creating this superposition where you have a single atom that is in both states more or less at the same time at a certain probability, similar to a qubit, right? And then when you measure it later on, you can then kind of see, probably by some emissions or something like that, has it been in one state or the other. And now the probability of these two states, in which state you will actually measure the atom finally, this can be influenced by accelerating the system in one direction or the other. And that's extremely exciting. So you're basically manipulating the atom itself by applying acceleration to it and then reading this out. And thereby you change the superposition probability, and thereby you can measure acceleration. And of course, this is extremely precise because it is using very much the smallest units, right, the atoms, to measure this. And let's say everything is kind of known in an atom, right? There's no such thing as a drift because it is basically just a single particle system. So there's nothing that can drift in there because you're talking about a single quantum object. So from my point of view, very exciting. There's more explanation of how this works and why that makes sense and how this is being built in the lab. I'm not going to go into the details of that, but again, I think a very interesting application, a very interesting quantum sensor that is being built. Also gravity, we see here, gravity is used in quantum gravity sensors to provide valuable information about underground infrastructure. So that might be interesting for exploring, for example, the planet, finding resources and stuff like that, identifying new mines and whatnot, right? So another one of these quantum sensors that might actually already contribute to value today. Again, I'm not going to go into all of the details, and as I mentioned, there are also some nanotechnologies down here. I'm not going to talk about these today. What I'm going to do is we are quickly going to check out the About Us part of the company to learn a little bit more about what company we have here and how they identify themselves before we then wrap up today's video. So about NKT Photonics, solutions for innovators, technology can transform our lives. It was true with the invention of penicillin, electricity, and the internet. Today, the transformation continues with amazing innovations such as autonomous electric cars, smartphones, quantum computing, artificial intelligence, stem cell and cancer research, renewable energy, and even space exploration. NKT Photonics customers are visionary innovators within these fields and more. They are changing the world through their innovations, and we are ready to deliver the cutting-edge solutions they need, solutions for innovators. We have lasers in space and deep under the oceans. Our products run in clean rooms and on oil rigs at the sea. We seed the world's largest laser fusion experiment and power thousands of the most advanced microscopes on the globe. The aim to make a difference in the world, and we aim to make a difference in the world and are involved in projects that will transform the way we live through life science, renewable energy, and the basic understanding of the universe. With over 20 years of expertise, IP, and experience in NKT Photonics strives to continually be the market leader in everything we do. Established in Denmark by scientists and engineers, NKT Photonics is based on a foundation of innovation and passion of photonics. We are the leading supplier of high-performance fiber lasers and photonic crystal fibers. You can trust us to keep pushing the boundaries of what is possible with fiber and laser technology. Our main markets are medical and life science, industrial, aerospace and defense, and quantum and nanotechnology. Our products include supercontinuum wide lasers, low noise fiber lasers, ultra-fast lasers, and a wide range of specialty fibers. NKT Photonics is headquartered in Denmark and is subsidiary of Hamamatsu Photonics. Founded in Japan in 1953, Hamamatsu Photonics today has more than 5,800 employees worldwide. All NKT Photonics products are produced under our certified quality management system, certified under the ISO 9001 standard. We have an ISO 9001 certificate for all three production sites, NKT Photonics, and then certificate and enclosure, and the ISO 13485 certificate for our Swiss site. And then there's the Swiss certificate. Then here it mentions again the markets that they're catering to. There is links to the leadership team, to the history, photos, site locations, and corporate social responsibility as well. I think that is a good roundup of today's video. Again, in a time of a lot of quantum discovery and a lot of active work in this field, I think it is very important to also highlight that there are companies building basically the infrastructure on which this whole revolution is being built. It is probably similar to when computers started, where also a lot of silicon technology and the chips that we are using today started, where a lot of groundbreaking work had to be done and still is to be done today in order to create those technical wonders of silicon. So I think if the quantum sector is growing, and I think it will be, and it will start probably with the easier things and then go to the more complicated things, then these companies, they will also profit from that. And I think NKT Photonics is definitely one of the major, let's say, suppliers for everything related to optics in the quantum field. I hope you liked this video. If you find this very interesting, if you want to see more about those, let's say, more general and more like base level tool suppliers that the quantum industry needs, let me know down in the comments below. I'm looking forward to see you in the next video. Until then, bye bye.